Yeah, good afternoon, everyone. As Christophe said, my name is Benoit, and I will show you some results from my work with colleagues here at the Baltic Sea Center in Stockholm University, but also colleagues at other institutes on how we're trying to understand the effect of past agricultural practice here in terms of nitrogen and how this impacts eutrophication. So as Christophe pointed out, I'm currently in Denmark, and if you want to locate me more precisely, I'm right in the middle of this little red catchment you must see on the map to the top right. So yeah, big question, how can we deal with eutrophication? So to let you into the story, one way is to look at where the sources of nutrients that usually are external drivers to that process. So here I show you data to see what we can get from that. So we're looking, if you look at the graph, dates in years on the x-axis, and then the y-axis, I will show you the the major part of the nitrogen content in the stream that drains these 5 catchments, 3 of them in Denmark, 2 of them in Sweden. The N content going through the river per year, also normalized per area of cropland in these regions. So these 5 catchments were selected because they have quite dense agricultural use. So agriculture is expected to be one of the main contributors to the river loads. And historically, when eutrophication started to be considered a problem, people looked at where these loads were coming from, and there were investment to try to curtail point sources. But while you were doing that, you still see that loads remain high or increasing even. So part of the problem will have to deal with how we practice agriculture. And just a wink here to Isabel, who very helpfully tested all the technical issues to have me here today via Zoom. All the data in Denmark to the left that is not screened here was recently acquired like 2 days ago, so I can show you more today thanks to this trip, and I'm thankful for the opportunity to anyway be here in some way with you today. Yeah, so let's move on. So how can we look in a very simple way at how agriculture could contribute to the river loads of, in this case, nitrogen? So let's do some accounting. So now I'm focusing still again on the field areas in one of these catchments. So if I just go back quickly, I'll focus now on this catchment that's shown in the pink color here and a bit south of Copenhagen to exemplify some of my, the result. So we take the field area in that catchment and we try to account for in what forms or pathways nitrogen comes in. If you look at the acronyms here I have at the bottom, for example, if we can take it from the top, the red component is the N that is fixated by some plants who have a symbiotic relationship with microbes and can draw their nitrogen from the atmosphere. So that's a minor component of the budget that you see in red. If we move down to the next part of the stacks, you get this green color, which is atmospheric deposition. So through wet or dry depositions, we get some nitrogen landing on the field themselves. So that's another minor component of our budget. And then the bigger part, that's this blue stacks, which is industrial fertilizers that are used to help grow our crops. With a very big increase through the 60s, 70s, high plateau in the 80s, and then some reduction in this area, as you see. And the final contribution to the nitrogen that we see on fields in this area, that's the application of animal manures that you see in the pink color. So all that's the positive part of the budget, and we use this to grow our crops, which is the, how should I say, yellow-brown part of the stacks that you see on the negative side of this graph. So what comes in minus what we remove, we get a net effect, which is this black curve in this catchment, which we think should drive, I mean, we expect it to drive the effect of agriculture on river loads. So we see that, yeah, some attention has been spent from the mid-80s, 90s to really clean up our act and be more efficient in using this nitrogen. But let's go back. So I still have here in black the nitrogen surplus that I just showed you. So what's supplied in excess to the fields. And how does it relate to the first curves I showed you, the N river loads, or the major part, which is the nitrate plus nitrite component of that nitrogen that's delivered by the rivers to the sea, here in the red curve. So do we see a response without doing any very hardcore trend analysis? I can say, I think we can see a somewhat decreasing trend, but the response is rather limited. It's definitely not proportional directly for a given year to the surplus that we think drives this nutrient loading. So what's our hypothesis when we see this? So it's not too complicated, but the idea is like this. By applying this excess of nitrogen through the years, we've built up stores. It can be in the soil, it can be in the surface waters, in the groundwater, in the catchment. And even if you start decreasing your surplus of nitrogen over agricultural land, you have some delayed effects and delayed release of those old stores. So you're still paying for old sins, if I can express myself in this way. And that raises questions. So, well, first of all, how much nitrogen is there stored in the landscape that we expect to see come out? And for how long will these impact the river loads that you see here in red? So that's where we try to investigate. Okay, so how can we try to understand and quantify those legacies? Well, what I'm going to show you today is it's a heavy use of models, as simple as possible, but yeah, a modeling attempt. So basically building this box with different components and their relationships that could translate one of my drivers, the N surplus, into the right nitrogen river load. So how can we design this box? So first question, how much is there? That's a question I already asked. And how much do we start with? You can do local measurements of N content in some soils, but it's hard to get the overall, to be sure about the overall estimate of the whole catchment. So the way we usually proceed in that context is to try to go as far back as possible in time, so that if we make mistakes at the beginning in these estimates, they should hopefully disappear through time, through the first years we run the model, and by the time we reach the period we're mostly interested in, which is present actions and recent years, we should be home free and away from this original uncertainty. Also, there is, it makes the exercise slightly more complicated, but there is added value to trying the model over a long period of time to see if we grasp what we think are the right kind of evolution in the system for the quantity of nitrogen in the soil and rivers and groundwater. Another question, what external parameters or drivers should influence how much this box retains some of the surplus or lets it come out as river loads? So here are some ideas. I don't mean to be exhaustive here, but the history of land use will be of interest to us. There will be other pathways where nitrogen can exit the system here to the atmosphere. So the eutrophication, that big blue arrow I just added. And as I'll show in the coming slides, strong effects due to hydrology and how we implement drainage in our agricultural soils. And also best practices and policies as they are adopted will obviously have a strong effect on how this box should regulate the fluxes from one end to the other. I will not go into very much details about the intricacies of this system. If you want more details, I refer you to this publication by colleagues in the US. There is much more to be found there if you're interested in details. So effects of hydrology was actually quite simple. Here I show you a graph where in black you see the mean annual discharge for the river in that catchment in cubic meters per day, per second. And in red, following the other y-axis, I show you what I showed you before, the river load. So this is not an example where I tried to match the dots, the data dots with the curve. It's just to show you that there is a strong correlation when I have a very high river load some year. It's usually because I have a very wet year where a lot of precipitations produce a lot of discharge and we flush the system rather strongly. So a lot of the variability in the river load is due to variability in weather for a certain year. And you see here an open door if you have climate scientists who want to collaborate with us. This creates a direct interaction if we talk about climate change. How will this affect the response of legacies in the catchment if the discharge is, I don't know, increasing by 20% or such considerations. Also, for people like me who come from the field of classical hydrology, I'm not an agronomist by training, you should always remember that you're not dealing with a very natural landscape, even though it might look that way. In some cases, up to half of it is actually artificially drained by networks of pipes that have been installed under the fields, which have a tremendous effect both on what we should, what the transit time should be through. Here you have a simplified depiction through each of the components of the model, but also impacting the biogeochemistry that the nitrogen is going through. For example, if you have a water-logged soil, denitrification will happen in a different amount than if you have a very well-drained soil. So very big impacts there where we should try to account for. So that was the effect of hydrology. Then here I won't go into details, but obviously all these effects are also impacted strongly by the adoption of relevant policies for farmers. So I borrow here a table from Aronson and Jonsson that shows you a summary of some of the legal frameworks that have been put in place in Sweden. Sorry, this is in Swedish. And obviously some of these measures should translate to different parameter values or different inputs to our model that you still see here at the bottoms. For example, rules on manure management and how many animals can be present at a certain location will have direct impacts on our end surplus. We should check that the data we get our hands on agree or disagree with what we expect from policy. Are they effectively put in place or not? Another example, this höst eller vinterbevuxenmark, so catch crops, maybe I should say this in English. So the choice you made to leave the soil bare or to put a crop during the winter, not for the crop per se, but so that the crop takes up nitrogen that would maybe leach in another context without that crop, should inform our choice of the parameters in the model. So there might be a time period where we model with a certain best practice, which doesn't really implement that measure, and a second time period in the model exercise where we assume someone has done something about it. Yes, I will wrap up. Yes, so I will wrap up. I will try to wrap up quickly. So what we do, we make guesses about 10 parameters in this type for this type of model. Test random combinations of them and see if they agree with the red dots that I showed you before, the river loads. So, and here I do this until I get 1,000 models that behave, I think, fairly well. So they follow the dots. How much can it tell us about how much nitrogen? So that was one of our questions. You see here that you cover a rather wide envelope of models that behave well between those two dotted lines. So we haven't learned yet too much from this work. We need to find other ways to constrain the system so that we can arrive at less uncertainty in our understanding. I think I will skip that part. This is going into more details about but wrapping back to what I showed you in the beginning, why do we do this? So I showed you this past data about the river loads. We think that if we get a better understanding of legacy stores and their dynamics, we're better able to predict the future of those curves, depending on what assumptions we make for future adoption of best practices. And also, for example, for climate change scenarios. And why do this? To help our colleagues who look further downstream in the coastal areas and open sea areas get their hands on realistic drivers for the eutrophication itself. So yeah, thank you for your attention. Again, here are all the colleagues, maybe not all actually, but the main colleagues who've been involved in this. I'm happy to take questions either now or if you want later, you have my email also up there.